So welcome back. So in this video we are going to be handling benzene and its derivatives. So the previous video was about benzene as applied to organic chemistry. So in this video we are going to be looking at its derivatives including phenol, methylbenzene and phenylamine. So this video is presented to you by Yusuf, and you're advised to subscribe to the channel and share the video to your friends so that you can all benefit as a group. We are going to be starting with methylbenzene. So methylbenzene, its molecular formula is given as CCC6H5 and then attached to a methyl group which is represented by CH3. So its structure or its molecular structure can be written in this form. It has a benzene ring and then it has a methyl group attached to the benzene ring. So this one, the AUPAC name or the name that you're supposed to be presenting in your exams is called methylbenzene. This taurine is a nickname and you're not supposed to present it anywhere. However, when UNEB is setting for it, it's allowed to use this word so that it can trick some of the students. But whenever you want to bring taurine, always use methylbenzene. So looking at the synthesis of methylbenzene, we are saying that one, it can be synthesized from Fidel-Crafts alkylation reaction. And here we are saying by alkylation of benzene with an halogen methane, alkylation of benzene with halogen methane in presence of an halogen carrier can yield you taurine or methylbenzene. So some of the halogen carriers that we have aluminium chloride, we have aluminium bromide, and we have iron bromide among others, but mostly we use iron chloride. So this mechanism or synthesis involves writing an halogen methane. Halogen methane, you are saying that it must be either iodomethane, or it can be bromomethane, or it can be chloromethane in presence of any halogen carriers. So here I used aluminium bromide, but mostly you can use aluminium chloride. So you'll be forming methylbenzene or taurine. This position is independent. One can put the methyl group here, one can put it here, one can put it here. This is what you call resonance. So looking at the mechanism of that, just like previously, the bond between carbon and bromine breaks off, and the bromide ion is taken up by our halogen carrier to form a complex which is aluminum tetrabromide and serving a negative charge. So you also form your methyl group, but this methyl group, I want you to notice that it is positively charged. I forgot to indicate the charges. Now what this does is that the bonding electrons from the benzene ring, they come for this electrofield. Now in coming this electrofield, they form a bond. So this carbon has lost its bond, that's why it's getting positively charged, and this one is having excess bonds. So it gets rid of one bond. So it gets rid of the hydrogen bond to replace the bond which was used to bring the methyl group. And then after losing that hydrogen atom is going to be gained by our halogen carrier, and it bonds with the bromide ion that was carried with our halogen carrier. So that means that our total products is going to be hydrogen bromide by getting the hydrogen atom which was got rid of, and then plus the bromide ion which had combined with our halogen carrier. In total, all they add up, they react and they give us hydrogen bromide. Now this bond breaks, and then to neutralize this carbon which was present here, that's why we form our taurine here. Of synthesizing taurine or methylbenzene is that you can use bromomethane, but this time around you don't need an halogen carrier. What you need is sodium in dry ether. So you're saying that by Watt's reaction, bromobenzene is reacted with bromomethane, and it's going to be in presence of sodium which is put in dry ether. So that's why you're having these conditions. So your reagent is bromomethane. Now also sodium is involved as a reagent, but dry ether is a condition, that's why it's below the arrow. So you'll be getting your methylbenzene. Now let's look at the reactions that methylbenzene gets involved in. Now first of all, before we go to reactions, we are saying that we are first going to look at the effect of the substituent group on the reactivity of the ring and the direction of the incoming group, so that we can understand fully how we shall be reacting methylbenzene with different compounds. Now we are saying that the positions on a benzene ring in reference to a given attached group are going to be labeled with numbers like 2, 3, 4. Now these are going to be in reference. If at all, take for instance, if at all X represents the methyl group on taurine, that means that the subsequent group that you are adding, if the group is going here, is going to be in position number or carbon position number 2, because we start counting from this carbon or from the vertex where the methyl group is attached. So the group that we shall be adding is going to be on position number 2. If it gets added to position number 3, just like we are going to be looking at these rules, is going to be on position number 3. And in the naming, we are going to be following the same naming principles or nomenclature principles like we have been following them in the previous videos. So you're saying that the position numbers 2, 3, 4 are also called ortho. Now ortho means 2. Meta is going to mean 3, and then para is going to mean the 4th position. So that means that here, this is the 2nd position, that's why it's called ortho. This is the 3rd position, that's why it's called meta. And then this is the 4th position, that's why it's called para. Now the same applies this side. You can either be counting coming from this side anti-clockwise, or you can be counting going to clockwise. They are going to be the same naming for as long as your reference is from the methyl group. Now we're saying that electron donating groups, now pay attention to this properly. Electron donating groups, what we mean here is that those groups with a positive inductive effect, groups that donate electrons to the benzene ring, in other words, the ones that take away, they are called negative inductive effect. The ones that donate electrons to the benzene ring are going to be called positive inductive effect groups. So positive inductive effect refers to, or a group that has a positive inductive effect is that group that is going to be donating electrons to the benzene ring. And a group that has a negative inductive effect is that one that is going to be taking away electrons from the benzene ring. So pay attention to that. Now you're seeing that electron donating groups or positive inductive effect groups are going to be activating the ring. And therefore, we expect to be adding such groups to the ortho and para positions or directors. So that means that if you are given a reagent, and the reagent that you are going to use is going to provide an electron donating group or a group with a positive inductive effect, that means that on your reaction in the products you should give, they must either be for ortho or para positions, as we are going to be looking at the examples. So you're saying that electron withdrawing groups, I've told you for electron withdrawing groups are going to be those groups that have a negative inductive effect, and therefore they are going to be deactivating our ring. And therefore, for those ones that deactivate, or the ones that withdraw electrons away from the benzene ring, you're going to see that they are going to be occupying the meta position or the 3rd position. Or position can also mean directors. Now here are examples. These are examples of these groups that are going to be directed to ortho and para positions. So groups that direct ortho is the 2nd one, and then para is the 4th one. So that means that whenever you're having a reagent and it's giving you any of these groups, either phenylamine or, in other words, anything that does not contain more than one oxygen atom. To memorize this earlier, the easiest way to memorize it before you advance is that you should remember that those ones that are going to have positive inductive effect, they must not, their compounds in most cases, they shouldn't exceed one oxygen atom. And those ones that are going to be directed to the methyl, in most cases, they should be 2 oxygen atoms or more. So be knowing that. That's a very easiest way to differentiate the two. So the ones that go to the third position, they must have 2 oxygen atoms or more. And the ones that go to the second or third or fourth positions, they have only 1 oxygen atom or without. So if you go to the groups that direct to the meta, or that will be to the third position, if you look at nitrogen dioxide, if you look at this compound for the carboxyl, if you look at this compound for sulfide, all these ones are having more than 1 oxygen atom, and an exception is that for anhydride. But also, it's going to be very difficult to get a reagent that gives you such a compound. So in most cases, you are going to be dealing with this. So always remember that for you to get the third position activated, you must have an electrophile or a neutrophil which has more than 1 oxygen atom. And always remember that those ones that are going to direct to the ortho and para, they are going to have only 1 oxygen atom or less. So that's a very good way to remember and memorize that. So if you go to the notes, in the note you are saying that the halogen groups, the amino group and hydroxyl group, all have electron withdrawing effects. And electron withdrawing effects, I told you that these ones include the negative inductive effect. Now, those ones are the groups that are negatively charged. For example, the chlorides, bromide halogens, halide ions are going to have a negative inductive effect. That means that they will be, since the atoms are attached to the carbon and they are more negative than the carbon, but they are ortho and para directors. Why one would think as meta directors? Now we are going to be looking at this more, but since I gave you a general summary of where ortho and para should go, we shall be looking at this under explanation questions as advanced topics to be looked at, because also the questions are examined and you are required to give a detailed explanation based on what you understood best. So you're saying that this is because the halogens, oxygen and nitrogen, have lone pairs of electrons. Now these lone pairs of electrons, now this is always the reason, and this is always the answer to most of the organic explanation questions. You say that most of the atoms attached to the benzene ring, they are going to have lone pairs of electrons. And those lone pairs of electrons do, they go and participate, they can participate with the bonds, or they interact with the bonds that are within the benzene ring, which you call the pi delocalized electrons. The electrons that are within the benzene ring, which you see as dashes, we call them pi delocalized electrons. So lone pairs of electrons on any atom attached to this ring, for example, chloride, bromide, or iodide, they interact with these delocalized pi electrons within this benzene ring. Now what happens is that, remember that this is a carbon to halogen bond. Once these electrons here interact with these ones, we do what we call strengthening of the carbon to this bond, and then weakening of the bond of the localized bond electrons between the benzene ring. And since they weaken, they are going to cause this benzene ring to be reactive to the ortho and para positions. But however, the simple reason to it, we are just going to say that this is because lone pairs of electrons on those atoms participate with the delocalized pi electrons that are within the benzene ring. And the effect of that is that it's going to tend to stabilize the ortho and para positions or directors. Here I said complexes at the expense of the meta complex. But if that complex is hard for you, you can substitute it to directors. If non-directors, you say positions. Number 1, reactions that are involved with methyl taurine. We are going to be looking at electrophilic substitution reactions of the ring. Now we looked at the types of reactions under the introduction of organic chemistry video, and we say that those things are examinable. Those reactions are examinable with relevant examples. Therefore, and you should know how to define each of them and know where each of them falls with specific examples. Now you're saying that note, the methyl group is an activating group, that means that it's going to be activating the second and the fourth positions, or it's going to be an orthopara director. Now you're saying that nitration, remember that I told you anything having any ion or any electrophile having more than one oxygen atom is going to be activating the meta position or the third position. That's why here we're having nitration, sulfonation, and Fiedel-Crafts alkylation and acylation and halogenation of taurine is the same as that for benzene, and the major products being the ortho and para products. Now we are going to be looking at the specific examples under that. So if you look at the physical properties of methylbenzene, we are saying that for methylbenzene, this is measured a colorless liquid, and you should be shown this in your laboratory. So it's a colorless liquid, and its toxic and long exposure causes anemia and also leukemia, which is the lack of adequate red blood cells. Now we are saying that also it is insoluble in water. It's insoluble in, but it is insoluble in water, or it is insoluble in polar solvents, and it's soluble in organic solvents. Its melting point is -95 degrees Celsius, and its boiling point is 111 degrees Celsius. Now note here, this note is emphasizing the point that the melting point of methylbenzene is lower than that of benzene, although methylbenzene has the highest molecular weight. Now why is this the case? Now the reason for that is because the planar molecules of benzene can pack closely together in a crystal, and therefore the cohesive forces are stronger, while in the methylbenzene, the methyl group prevents close packing of the molecules. So you find that benzene is more closely has molecules that are more closely packed. Therefore, to melt, it's going to require higher amount of energy in form of heat compared to that of methylbenzene, where the methyl group prevents the different molecules of methylbenzene from closely packing together, hence lowering its melting point. Now you're also having a question here. The melting point of methylbenzene is lower than that of benzene, although methylbenzene has the highest molecular weight. Explain. I think it's what has been questioned for here, but let's look at its solution. Go to the reactions of the side chain. Now the side chain, here we are going to be looking at the methyl group attached. So example 1, you are going to be looking at oxidation. When you are saying that reactions of the side chain, we are saying that reactions that are going to be involved specifically for this methyl group attached to the benzene ring. So you are saying that methylbenzene is oxidized by hot, strong oxidizing agents, for example, acidified manganese 7. Now I said in the previous video that I wrote acidified manganese 7 using this arrangement, but make sure you alter this arrangement. The acid ion must come last. So it should be manganese 7 stroked with the acid ion. That's how we write acidified manganese 7 solution. Or you can use acidified dichromate 6 solution. And what it's going to do is that it's going to oxidize it to benzoic acid. Like I've told you, alter this arrangement, but remain with the same states. So acidified manganese 7 oxidizes taurine or methylbenzene to benzoic acid. Also, methylbenzene is oxidized by mild oxidizing agents. For example, manganese oxide, acidified manganese oxide, or chromium dioxide dichloride, or which you can call also chromyl chloride to benzaldehyde. So you find those oxidizing agents that are not so strong, and the good one to use is always this one, because this one has no debate and it has no any conditions. So you just write your CrO2 and CO2, no conditions required, you get your benzaldehyde. So make sure that you write these symbols properly, and bonds should be attached to the elements or atoms they are leading to. Now if you look at the second reaction, you're going to be looking at halogenation reactions. Now we're saying that methylbenzene is halogenated with chlorine or bromine, but this is going to be only possible in presence of ultraviolet light to produce substituted products. So when you're having methylbenzene, you react it with chlorine in presence of ultraviolet light, you'll get benzene chloromethylbenzene. And I told you, when you're writing this in your exams, always avoid abbreviations. So UV, write it as ultraviolet light. Always remember that. Another reaction, you're going to be looking at an hydrogenation reaction. So you're saying that methylbenzene is hydrogenated, and this is done at 200 degrees Celsius. I didn't put that temperature, I just said heat, but you're not supposed to do that. These reactions are supposed to be given their specific temperature. So you cancel out heat and then you substitute it with 200 degrees Celsius. So saying that methylbenzene is hydrogenated with hydrogen, which is done in presence of heated nickel catalyst to form methyl cyclohexane. So if you get hydrogen in nickel as a catalyst, don't write cat. I was just simplifying my notes. So if you want to write it, you can either leave it out and just say hydrogen stroke nickel at 200 degrees Celsius. To hydrogenate a benzene ring, you do it at 200 degrees Celsius, but if it's aliphatic, you do it at 150 degrees Celsius. So you get methyl cyclohexane. Now let's look at another derivative of benzene, which is going to be phenol, and in this case, its molecular formula is written as C6H5OH. Now this phenol can also be called as hydroxybenzene. Now we are saying that synthesis of phenol is going to involve the following. Number one, first of all, we can synthesize phenol from phenylamine. Now we are saying that the phenylamine is going to be diazotized to benzene diazonium chloride. And here we are going to be using sodium nitrate solution followed by concentrated hydrochloric acid. And the temperature here is very specifically 0 degrees Celsius. Now here we are going to follow it by hydrolysis to obtain our phenol, and we do this hydrolysis by introducing water and we warm. You can either write warm or you can write 50 degrees Celsius. So when you get your phenylamine, which is also called aniline, you introduce sodium nitrite in presence of concentrated HCl at a temperature of 0 degrees Celsius. You are going to get your benzene diazonium salt. Now notice that above this nitrogen, there must be positive charge, and on this chlorine atom, there must be a negative charge, because there is an embarrassment in the charges here. Now what we do after doing this, we hydrolyze, and we do the hydrolysis by introducing water, and then you heat at 50 degrees Celsius. You end up with your phenol, as presented there. Now we are saying that by reacting aromatic halides, now note that here, this water may be acidified sometimes. That's why you find some textbooks saying that this one can also be acidified water, because the acid ion from the acid reacts with the chloride, and then the water functions with the diazonium salt to give us phenol. So someone else can use acidified water. I know some of you may have a concern there. So we are saying that number two, by reacting aromatic halides with sodium hydroxide, and we do this in the presence of copper 2 chloride catalyst. But this is done specifically at a temperature of 300 degrees Celsius and then a pressure of 200 atmospheres, and this is followed by dilute amino acid, like we are going to be looking at it. Reaction is casually important because many of you miss up this reaction. Many of you want to convert this to phenol directly, and the mistake you do, you write sodium hydroxide in aqueous medium and you heat. That reaction is not feasible because we told you that lone pairs of electrons on this chlorine atom, they are going to come and interact with the delocalized pi electrons within this benzene ring. Now once they do so, they strengthen the carbon to chlorine bond, and therefore this chlorine cannot be substituted for by just the hydroxide from that sodium hydroxide you want to use. So that's the reason, and it's awarded around 3.5 marks if at all that question is to be examined. Now we're saying that the simplest way to do that, now notice that here, the alternative reagent for this one, let's try to shorten it. So it's going to be sodium hydroxide, editing the reagents for the first place. So it's going to be sodium hydroxide, and the conditions here, we are going to be having 360 degrees Celsius, comma, and the pressure that we are going to be using this time is going to be 115 atmospheres, 150 atmospheres. So make an adjustment there. So we're going to be using sodium hydroxide, which is present in aqueous state, but you heat at 360 degrees Celsius and you apply a pressure of 150 atmospheres. So you're going to end up with sodium phenoxide. Sodium phenoxide is what you're seeing here. Now, to convert sodium phenoxide to phenol, you use diluted HCl. But just like I said, when you're writing in your exams, always make sure that this word dilute is complete. This is just I'm simplifying my work. So just write dilute HCl, so you end up with phenol. Now also the shorter reaction. Now this one is known by a few of you, but it's also highly acceptable. You can get nickel in steam at 425 degrees Celsius to form phenol straight away from any. Now here it's not strictly chlorobenzene, it can be any halogen. It can be bromine, it can be bromobenzene, or it can be iodobenzene. You just need nickel in steam. Now if you don't put this state on water, you'll be marked wrong. We need to see the state. So it should be nickel in steam at strictly 425 degrees Celsius. Don't say heat because this reaction is highly specific. So it's going to be nickel struck with steam at 425 degrees Celsius to form phenol. And phenol is written in this form. Now you're saying that number 3, you can also get phenol by reacting sodium salt of benzene sulfonic acid with sodium hydroxide, and this is done at 300 degrees Celsius, followed by diamino acid. The diamino acid is to help you convert sodium phenoxide into phenol. So if you're having a salt of benzene sulfonic acid, you react it with sodium hydroxide, which is at 300 degrees Celsius, you form sodium phenoxide, and then you hydrolyze it with diluted HCl. After the next exams, you always write this word in full. We don't have this short form being marked on the marking guide. So write diluted HCl, so you'll be forming phenol. Now you can also form phenol strictly through Schumann process. Now you're saying that benzene is first alkylated in this case, and this is done with propene using concentrated phosphoric acid or aluminum chloride catalyst to form Schumann. Now the Schumann that has been formed is oxidized by oxygen to form Schumann hydroperoxide, that is then hydrolyzed by dilute sulfuric acid. And when you do so, we are going to be getting our phenol. But we not only get phenol, we get also propanol, which is also called acetone. So this question, this topic is highly set in paper 1, because in paper 1, when they set for the things, they tell you to complete and write the products that are going to be formed. And for you to get all the marks, you are supposed to write each and every product that is formed for you to attain 4 marks for that specific question. Look at this. You have your propene in presence of concentrated phosphoric acid. You are going to form a product like this. So this product isomerizes to this. And then after that, you hydrolyze it with dilute HCl. When you hydrolyze it with dilute sulfuric acid, you'll be forming phenol. And it's not only phenol, but you also get propanol. So let's look at the physical properties of phenol. Physical properties of phenol, first of all, it's a colorless crystalline liquid. And the other one is, now this is a mistake. There's no colorless crystalline liquid. It's a colorless crystalline solid. Make an adjustment there. So you're saying that it's also slightly soluble in water, but very soluble in organic solvents. Its melting point ranges between 39.5 to 41 degrees Celsius, but its boiling point is 182 degrees Celsius. Now let's look at phenol, all the reactions that are involved in phenol. So you're saying that number 1, you're going to be looking at the reactions of the ring itself. Now we are saying that, just like I said previously, The hydroxyl group is a deactivating group, but an orthoparadirector, just like I gave in the example. Nitration, sulfonation, Fidel-Crafts alkylation, and acylation and halogenation of phenol is going to be happening the same way like that for benzene. That means that the same mechanism we did for benzene are the same mechanisms that you are required to do here. But here, you just need to know the position to which the product is getting, the electrophile is going to get to. So I'm saying that the major products are going to be ortho and para products. Now you're saying that nitrophenol is obtained with dilute nitric acid, as you are going to be looking at it in details. With concentrated nitric acid, we shall be yielding 2,4,6-trinitrophenol. I've said that you're going to be looking at this in details. So number 2, let's first look at the reactions of the side chain. And the side chain, we are saying that reactions that are going to be involving the hydroxyl group that is attached to our benzene ring. Now notice that here, the vigor of reactions of phenol is going to be less compared to that with alcohols. And the reason for this, can you reason this out? The reason for that is the same reason. Just like I've told you, everything having a benzene ring, they have the same reasons. So here you're going to find that lone pairs of electrons that are present on this oxygen atom are going to come and interact with these delocalized pi electrons within this benzene ring. Now as they do so, the carbon to oxygen bond is weakened or is strengthened. And then the OH group here, the oxygen to hydrogen bond is going to be weaker. So the main reason for that is because lone pairs of electrons on the oxygen atom, they interact with the delocalized pi electrons that are present within the benzene ring. It's as simple as that, making the vigor of reactions of phenol less compared to that of alcohols. So first of all, reaction number 1, let's look at ether formation. Now when we are looking at ether formation, we are saying that phenol is going to react with halogen alkanes, but this is going to be in presence of alkalis, because phenol itself is acidic. So every reaction involving phenol, or every reaction where you see a benzene ring is attached directly to an hydroxyl group, I want you to understand that the condition that must be present must be sodium hydroxide. Reason for that, I told you, lone pairs of electrons on this oxygen atom interact with the delocalized pi electrons within this benzene ring. Now once that happens, this bond between carbon and oxygen is strengthened. But as we strengthen this bond, we are going to be weakening the bond between oxygen and hydrogen. So that means that in solution, phenol is generally acidic because this bond is weak. So these hydrogen atoms are going to be easily released off into solution. Now as they are easily released off into solution, it's going to make the general solution acidic. So that means that for phenol to be reactive, there must be an alkaline medium. Now that's a good general example for that. Now let's look at the reactions. So we're saying that phenol reacts with halogen alkanes in presence of alkalis to form ethers. And for example, we're having bromomethane here reacting with phenol in presence of sodium hydroxide. Whenever I use sodium hydroxide, we always give it a state. Mostly we use it in aqueous. And then we are going to be forming methyl phenoxide. Now let's look at the mechanism for that. First of all, sodium hydroxide is a very strong base, so it fully ionizes to sodium ion and hydroxyl ions. Now what happens, just like I've told you, that the bond of oxygen and hydrogen on phenol is very weak, it easily breaks. So oxygen takes out all the bonding electrons and it gives us a phenoxide ion. And then this hydrogen ion that has been got rid of is came for by the hydroxide ion that came from sodium hydroxide. And they team up to form water as a molecule. So sodium phenoxide, so phenoxide here as an ion requires stability, so it needs to bond with an electrophile. So what happens is that the bond between carbon and hydrogen breaks off to bromine, since bromine is more electronegative than carbon. And then the lone pairs of electrons on the oxygen atom, they come and form a bond with this electrophile of methane that has been formed. Now in your mechanism, you can always skip this slow step. This is just for details, but you can always keep it in your notes. And then you come straight out to here, showing that this oxygen formed the bond to give us the methyl phenoxide. The other product that is going to be there is going to be the bromide ions. And I told you in mechanism we don't leave bromide ions unreacted. So these bromide ions are going to come and react with these sodium ions. So what is going to be the total product formed? That means that you are going to form another product of sodium bromide. You can supplement it on your mechanism as you're writing. So we are going to form another product of sodium bromide. So in this reaction, you have seen that you're going to form methyl phenoxide, you're going to form sodium bromide, and you're also going to form water. So there are 3 products. So since if such a question is set in your paper 1 chemistry, you are supposed to present all those 3 products so that you can get all the marks. So looking at ester formation as another type of reaction, we are saying that here we are going to be looking at it from acid chlorides. So when you're having an acid chloride and then react it with phenol, you are going to form phenylethanoate, which is an ester. We show that something is an ester when you're having 2 R groups joined by 2 oxygen atoms. So the mechanism for this, we shall be looking at it later. But let's look at another reaction for organic acids. We shall be looking at this one more in details under the topic of esters. So from organic acids, you can react phenol with an organic acid in presence of an alkaline medium. Just like I told you, most of the medium that you are going to be needing when you're dealing with phenol is going to be an alkaline medium. So you're always going to be seeing this hydroxyl appearing. Or when you're in your mechanism or your synthesis reactions, make sure that the condition that is valid for phenol is always going to be alkaline medium, since the compound is acidic in nature. So when you react the two, you're going to be having phenylethanoates. Now you're saying that note, this is an esterification reaction, first of all. So note that esterification of phenol with inorganic acids does not occur in acidic medium, just like alcohols. Remember that when you reacted alcohols with carboxylic acid, we are doing it in acidic medium, but for phenol it's different, because phenol itself is acidic in solution. So the medium it requires is going to be sodium hydroxide, or it's going to be requiring an alkaline medium for its reactions to take place. So looking at part C, we are saying that phenol also reacts with phosphorus pentachloride to form chlorobenzene. So this reaction is possible. This reaction is possible, but the reverse, to substitute this chloride ion with hydroxyl, is not possible. That's why I told you have to use the other conditions of sodium hydroxide at 360 degrees Celsius and 150 atmospheres. But going this way, converting it to chlorobenzene, is generally possible, and we used phosphorus pentachloride. Although there are other halogen givers that you can use, but this one is more lenient, or it's more user-friendly since it doesn't require any conditions. Looking at part D, we are saying that also phenol reacts with sodium metals, and it does this to form sodium phenoxide and hydrogen gas. So balancing this equation, you just put a half here in case balancing is required, because what this sodium does is that it just replaces one hydrogen atom. So you end up with sodium phenoxide as your main product. Now looking at part E, we are saying that phenol reacts with heated zinc dust, and when we do so, we shall always form benzene. So having phenol and then you heat it with zinc dust, you form your benzene as the main product, and you're going to form your zinc oxide as the minor product. Now you can also look at reaction F, and they're saying that here phenol forms a weak acidic solution, and this acidic solution is going to react with sodium hydroxide to form sodium phenoxide and water. So here you get phenol, you react it with sodium hydroxide, and then you're going to form sodium phenoxide and water. I already explained this one, that phenol forms a weak acidic solution. I believe that everyone understands what this means. I've already explained it in terms of interactions of the lone pairs of electrons with the localized pi electrons that are present within this benzene ring. Now you're saying that when phenol heated with ammonia, and when phenol is heated with ammonia in presence of zinc chloride at a temperature of 200 degrees Celsius, we always form aniline. And this reaction is very important in your synthesis. If at all you can memorize it, you are very good to go. So when you're having phenol You heat it in presence of ammonia and zinc chloride at 200 degrees Celsius, you're going to form what you call aniline, or you can form what you call phenylamine, and it's a condensation reaction. That's why we are releasing water here. We'll be looking at hydrogenation reactions. Now you're saying that phenol is hydrogenated. I told you hydrogenation of benzene occurs at 200 degrees Celsius. So it's hydrogenated in nickel catalyst in presence of with hydrogen in presence of nickel catalyst, and you're always going to be forming cyclohexanol. So if you're having 3 hydrogen atoms in nickel, you can neglect the word catalyst or cat, but which you cross out heat and you make sure that it's 200 degrees Celsius. That's the temperature we hydrogenate benzene rings at. If it's aliphatic, we hydrogenate it at 150 degrees Celsius. So always remember that. Now let's look at some of the confirmatory reactions or tests of phenol. Mostly these ones are employed in the laboratory. So first of all, we are going to be looking at the reaction with bromine. Now here, the reason why I brought up this one first is because sometimes when we give you organic calculations, we tell you to write different isomers. And in those different isomers, we give you a given characteristic, and we tell you to identify a specific product out of the isomers that you gave. So this is where that is important from. And the common one is, if at all we want you to give us phenol as one of the isomers, we tell you that phenol reacts, the compound that you form reacts with bromine and form a white precipitate. So you are supposed to find out what is that white precipitate named like, or what's the opaque name for that white precipitate. So always when you react when you react bromine with phenol, you are going to form a white precipitate, and the white precipitate that you are forming is going to be of 2,4,6-tribromophenol. And you're having these products. So phenol reacts with 3 bromine atoms or molecules to form 2,4,6-tribromophenol solid, which is a white precipitate. And then you're also going to form 3 molecules of hydrogen bromide. Now when you're writing these equations, it's better to balance them. Now note that this reaction confirms phenol only when aniline is absent. So that means that they give the same test with aniline. So you cannot differentiate phenol from aniline by using bromine as a reagent. Now looking at part B, we are saying that reaction of neutral iron thiochloride solution. Now with neutral iron thiochloride solution, we are saying that phenol reacts with neutral iron thiochloride solution to form a violet solution, or someone can call it a purple coloration. And this reaction is the only valid reaction that confirms phenol. So if they ask you for a reagent that distinguishes phenol from any of other compounds, it's strictly neutral iron thiochloride solution. Now the mistake most of you make is that when you're writing this reagent, you stop on neutral iron thiochloride. This word solution must be present. So it must be neutral iron thiochloride solution, and the observation you get a violet solution, or you can say a purple coloration is formed. And this reaction is the only reaction that confirms phenol. I repeat. So going to another part, you're saying that reaction with sodium hydroxide solution. Now phenol is soluble in sodium hydroxide but insoluble in sodium carbonate. Now this distinguishes phenol from a carboxylic acid. Phenol, first of all, phenol is soluble in sodium hydroxide because I told you phenol is acidic in nature, and acids react with bases. So that means that for phenol to react with sodium hydroxide, it simply indicates that phenol is acidic in nature. But however, phenol is going to be insoluble in sodium carbonate. Reason being, phenol does not react with sodium carbonate as a solution, but all carboxylic acids react with it. Now, in your practicals, this is going to be very important, and this is how you differentiate phenol from your conclusions, or this is how you are going to be narrowing your deductions. So you should know that phenol is unreactive to sodium carbonate, but however, carboxylic acids are reactive to it. And the reason why you are comparing phenol and carboxylic acids is because both of them are acidic in nature, and when you're in your practicals, you can't distinguish that this is phenol or this is a carboxylic acid unless you test the two with different reagents and see how each of them is testing with each other. Now we also have what we call coupling reactions. Now this one, we are saying that phenol reacts with benzene diazonium chloride, but this happens in presence of an alkali to form a brightly yellow azole dye. So when you're having benzene diazonium salt in phenol, in alkaline medium, you're going to form a brightly yellow azole dye, which is written like this. And this one is highly examinable in terms of synthesis. We should always remember the conditions. When you're writing phenol with diazonium salt, you're going to be using alkaline medium. Reason being, phenol is generally acidic in solution. Looking at aminobenzene as one of the last derivatives of benzene. So aminobenzene is also called phenylamine, and its molecular formula is C6H5NH2, or it can be written as this. Now you're saying that if you are to look at the synthesis of aminobenzene, number one, aniline, aminobenzene is also called aniline, and it's also called phenylamine. So you should understand that these words should not be new to you. So aniline or aminobenzene or phenylamine is prepared by reduction of nitrobenzene using a mixture of tin in concentrated hydrochloric acid followed by hot sodium hydroxide. Now this is the very common reaction, and you should always be remembering this at your fingertip at all times. So when you're having nitrobenzene, the first reaction, that's why I'm putting here number one. So this is very important. Numbering is very important. Numbering your reagents. It shows that this one should come first and then the other one should come next. So you need tin in concentrated HCl. And number two, you need sodium hydroxide in its aqueous state. Whenever you use a base, give it a state. So sodium hydroxide in its aqueous state, and then you heat. Here you'll be yielding your phenylamine as the major product. Now you're saying that you can also form phenylamine or aminobenzene or aniline through Hofmann's degradation reaction. Now what this reaction does is that it eliminates or it removes what we call the carbonyl carbon group. So this carbonyl carbon group is eliminated whenever you're using Hofmann's degradation reaction. So looking at this, we are saying that the aromatic amide is heated with bromine, and this is done in presence of concentrated sodium hydroxide. Now this word is very important because it should be present. Now here I didn't include it, but you should put it somewhere here because you need to know whether your base is either concentrated or dilute. So you should put it there in your whenever you're writing your synthesis. So if you write bromine stroke with concentrated sodium hydroxide, and the condition here is heating. So you're saying that if you're having your amide, which is like this, now this is called benzamide. So if you're having benzamide, you heat it with bromine stroked with concentrated sodium hydroxide, and you heat. What it does is that it's going to remove this carbonyl carbon group, and then you are going to end up with your phenylamine or aniline or aminobenzene. Now number three, we are saying that by heating phenol with ammonia and zinc chloride at 200 degrees Celsius can also yield you aniline, or it can also yield you aminobenzene, which is the reaction that I already talked about in phenol reactions. So you heat at 200 degrees using reagents of ammonia that are present in anhydrous zinc chloride. So you'll be forming your aminobenzene or phenylamine or aniline. And also water is given off since it's a condensation reaction. Reactions of aminobenzene, we are saying that the reactions on the ring, remember that this amino group is a deactivating group just like other groups that we have been looking at. So it's a deactivating group is going to be an orthoparadirector whenever we react it with anything. So nitration, sulfonation, just like benzene, are going to remain the same, implying that they are the same mechanisms. That's why I didn't repeat them here. You just need to know the position to which the atom is going at, and then you follow the mechanisms that are engaged in the benzene ring mechanisms. Now you're saying that let's look at other reactions. Other reactions, we are going to be looking at reactions with bromine. So aniline, just like phenol, they have the same reaction with bromine. So aniline reacts with bromine to form a white precipitate, and this white precipitate is going to be for 2,4,6 tribromoaminobenzene. So here you'll be having 3 molecules of bromine reacting with aniline to form a white precipitate of this in presence of hydrogen bromide. Now I'm saying that note, this reaction is going to differentiate aniline from benzene and other compounds and other aromatic compounds except phenol, because phenol and aniline or phenylamine, they all present the same observation, which is always going to be a white precipitate. So when you're writing this, you always put here state as a solid plus 3 hydrogen bromide, because 3 hydrogen atoms are substituted for. Remember that this is an electrophilic substitution reaction. Here we are saying that aniline reacts with nitrous acid, which is prepared and used in situ from sodium nitrate and concentrated hydrochloric acid, but this happens at 0 degrees Celsius because nitrous acid is not stable at room temperature. Room temperature, remember that it's about 25 degrees Celsius. So benzene diazonium chloride is always produced. So when you're having phenylamine, you heat it in sodium nitrite in concentrated hydrochloric acid at 0 degrees Celsius, you're going to form benzene diazonium chloride. Or some call it the benzene diazonium salt. Now it's a salt when the chloride is not present. We call it benzene diazonium salt. So this N2 has a positive up, and this chloride atom has chlorine atom has a negative on it. However, these charges tend to neutralize, that's why in minor I didn't include the charges. Then plus water, since it's a condensation reaction. To the end of this video, you're advised to share the video to your friends, and so that you can all benefit as a family, and success to those of you having exams.